we are getting into what's like really chemistry. Um, and in what I call the real chemistry, what we have here, I'm just checking a little note that's up here about benchmark because that reminds me that I have to get your benchmark together. Um, is that we have this thing called chemical reactions, right? I talked about combustion. I said there's other reactions we're going to learn. Before we go to learning about reactions and predicting them, we're going to talk about this thing about what does a reaction tell us? Besides what did you start with, what did you end with, what are the other relationships that exist in a reaction? So, in chemistry now, there are different ways of representing what goes on in a reaction. There is an English sentence with, full spelled out words. There is what I call the chemical reaction sentence, where you use formulas. That's why we spent time writing formulas, so you would know how to write down the chemical compound that was there that was reacting, and symbols to show what's going on. And then there's the particle diagram way of showing what's going on in a reaction. So this is getting more into what I call chem speak, because we don't write out long descriptive sentences to talk about chemistry. We represent them in symbols and chemical formulas to condense what we want to talk about, make it faster to talk about it, but also to represent one of the founding principles, one of the laws that goes on in science, which is called the law of conservation of mass. So we're actually representing that law when we write a chemical reaction. Oops, whoops. What happened? That's my fault. I hit outside the box. Can't hit outside the box. Okay, so I gotta scroll down now because I had to reopen it. Whoop. And where? So when you balance and look at a chemical reaction, you're looking at the relationship between everything in that reaction. So, in a reaction, we have what's called reactants, and the reactants are the things you start with. And those are, oops, I thought I had that on. Those are on the left-hand side of the equation. And then on the right-hand side, we have what we call products. Now, right now, because we're starting and doing baby steps, we're going to talk about always going what we call the forward direction, which is left to right. Okay? There will be a time when in, Christmas-ish, January-ish, where we will start talking about reverse reactions. So the forward direction goes left to right. So when we talk about the forward direction, that is the reactants on the left-hand side, products on the right. We can go the reverse direction, which goes right to left. And then it kind of flip-flops. Technically, if we go in the reverse direction, what we start with is the products, and they now become the reactants. And then what you make on the left-hand side is your new products, which used to be your reactants. Some reactions can do both, forward and reverse, at the same time. So you make a product, and then it decomposes, or changes. I shouldn't say decomposes. It can be a decomposition, but it doesn't have to be just a decomposition. So you go forward and you make your products, and those products then break apart and go backwards and remake your original reactants. So there is this, in some cases, forward and backwards. Now, in a chemical reaction, the arrow is the same as an equal sign, because the mass that you have over here, all the little atoms added up, will equal the mass over here. Okay, and that's where we say, oh, we have this equal going on. The stuff on this side has to equal the stuff on this side, whether you're going forward or reverse. Okay, so again, there's three ways. We have the English writing out the word way, we have the chemical speak way, and we have the particle diagram way. This is all the same. It's supposed to be D. This is all the same reaction. Sorry, brain fart. So, see, it says 2 hydrogen molecules. So, we put a 2 in front. That's this 2. And we have to remember this is diatomic. Oh, now this becomes big. You've got to be able to remember diatomics. Whoops, atomic. I was trying to go diamic, but it's diatomic. Here's O2, also diatomic. Now, it's kind of a little hint because we called it a molecule. And now we make 2 water molecules. See, here's the coefficient in the front. Telling me I have 2 of those. Now, what's interesting about this is if I count up my total number of hydrogen atoms, I have 2 times 2, which is 4 H's. If I say how many H's altogether are running around in this mixture, or I shouldn't say mixture, running around this reaction, running around in this pot that's sitting in front of us, then I have 2 O atoms. And on this side, look, I have 4 H's because I distribute this over here, and I have 2 O's because that gets distributed to him, and his subscript is known to be a 1. My number of atoms total on this side equals my number of atoms total on that side. And this is a nice little picture of it, although this isn't in color and you can't see the niceness of it. When they react, these 2 split, so do these. And they rearrange so you get an H, an O, and an H. Little bent, because this is a space-filling 3D molecule set. And so you can see the bend. And that's our particle diagram on it. Oh, I have another one there. Now, this brings apart this concept of balancing. And this is where you're going to see why you need to know diatomics. In balancing a reaction, it's like being on the playground in a teeter-totter, right? Because we will look at how much we have here, and we pick one thing at a time, and you go back and forth, and you say, how much do I have here? And then, I make sure I have the same number here. But then does that change something on this side? So it makes it too heavy, and then I got to go back over on this side and change something else. So you're literally going back and forth all the time. And it all comes from this law, the law of conservation of mass. And I'll throw in the energy in there too, because there's 2 laws that we talk about a lot, conservation of mass and conservation of energy. When we get done, it is really important, and when I say when we get done, when we get to April, beginning of April, you need to know what is conserved in a reaction. Ooh, why isn't it raining today? Come on. Oh, duh. Told you it's been one of those weeks. My brain just not functioning. Okay, what is conserved in a reaction? And here's the 3 things. Mass, which we're going to talk about today. Energy, which we're going to talk about soon. We'll mention it now. And this thing called charge. Okay, remember we had ions? And we have movement of electrons? Well, that's where this comes into it. The total, literally, ion charge on one side has to equal the total ion charge on the other side. And you can have free electrons depending on your chemistry, so you have to take that into account too. So everything, mass, energy, and charge is conserved. We're going to right now focus on a couple of them. When we talked a lot about the conservation of mass, we say that matter is neither created nor destroyed. It stays the same throughout the reaction. Now, you might have some mass turn into energy, but we never lose it. Okay, the mass turning into energy, that's what we do with nuclear chemistry. We're not going to get into that now. We'll go into it later. But for now, we're going to focus on reactions where really the mass pretty much stays the same. Any loss in mass will get converted to energy. And that's actually converted with E equals mc squared, Einstein's relationship. So even if you lose a tiny bit, that c squared is 10 to the 8th squared. So that makes a lot of energy. Okay? And that's why when we talk about chemical reactions, the actual possibility in a chemical reaction to lose mass is very slight. So we talk about balancing out your chemical reactions on paper so that when you do any type of calculation, you can predict how much you're going to make. Because we don't talk about losing mass in a chemical reaction. We will talk about it in a nuclear reaction, but not in chemical. Chemical, we say there is energy created in bond breaking and bond making. Like you got to put energy in to break the bond. You release energy when you make the bond. So we'll talk about that energy, but we don't talk about the nuclear energy. Nuclear energy, like I said, if this is what we talk about in terms of nuclear, E equals mc squared, you can have a huge energy gain or loss, and usually it's a production, so it gives it off. When you have a slight little change in mass due to nuclear reactions. In chemical reactions, we have bond energy, but that does not equate to nuclear energy. Nuclear energy is by far greater. Okay? Nuclear energy is much greater than a chemical reaction. Because it's nuclear. Two different reactions. So that's why in a chemical reaction we say the mass stays the same. Or is conserved. So how do we represent it? Well, we represent it by balancing. Are you going to have, and this is like a guideline over here, but I'm going to tell you that sometimes the guideline doesn't work that well. And you're going to do it so often that it will become, you're going to hate this word because I used to hate it when I was in school, and they'd say, intuitively obvious. It's going to become very intuitive. You're going to start to really get a handle on it and go, oh, I go here, there, and then I got it done. Okay? This is really important because what ends up happening is people get frustrated and they start to change the chemical formulas. Once a formula is written, you never, ever change it. So you never touch the subscripts of the formula to balance. What changes the coefficients. Okay, just the coefficients in the reactions get changed, not the formulas. All right, so if you're tempted to change that subscript, spank your little hand and say, no, don't touch the subscript, only use the coefficient. So here is a makeshift word equation. Nitrogen gas is added to hydrogen gas to produce ammonia gas. Right? So we have to go and look at that and say, all right, what's my formula for nitrogen? That's where diatomic comes in, right? Because know thy diatomics. Whoopsie, I did it again. I keep wanting to write with a highlighter tonight. Okay, know your diatomics. It is really important. Diatomics. Those wonderful 7 diatomics. So nitrogen's a diatomic. This is its formula, its natural state. That's how you write it. Its phase is a gas, so it goes in parentheses in small letters. And then you have hydrogen gas and ammonia gas. Now, I didn't know before I balance, I'm going to come to the 3. The 3 is there, but how it comes about is if we look at NH3, and I'm going to go to a whiteboard now so I can show you this. It can get too crowded on here. Taking forever. Oh, here we go. Right, so we had N2. Hello. Oh, I don't have my thing on my hand, that's why. Okay, N2 plus H2 gives, we can use the arrow, NH3. Oh, this is going to be fun in Google Docs, isn't it? We got to be able to insert an arrow. We got to be able to do subscripts. And we're going to have to do coefficients, okay? Now I'm going to look. Over here I have a 2. But here, I only got a 1. Now I cannot change that formula. Okay, I can't change it. That has to stay. The only thing I can do is change a coefficient. So if I put a 2 in the front, I now have 2 nitrogens on the right-hand side. But by putting a 2 in front of this, I also changed my number of hydrogens. I no longer have 3. I have 2 times 3, which is 6. So I come back over here, and I go, ooh, I have a subscript of 2. 6 can be divided by 2. I just need a coefficient of 3. So now if I look at my total number of atoms, I have 2 nitrogen, 2 nitrogen. I have 6 hydrogen, 6 hydrogen. And I'm now balanced. Okay? Let's see. I'm going to just shrink this. Right. So I'm going to go on to the next page, and we're going to do a few. Some are already done for you, but I'm going to walk through this. Ow. Let's see. Iron plus oxygen gives us iron 3 oxide. Right? Iron plus oxygen gives iron 3. So that had a 3 plus. Oxide, that had a 2 minus. Crisscross, 2, 3. Neaten it up, because AP can't stand charges written up there if it's a compound. So you step back and you look, is my equation written correctly given the words that I was given? Well, this is where you need to know diatomic. So hopefully you're like screaming at the screen, it's Lefty! That oxygen's diatomic! So I'd have to put a 2 here. Okay? Now I have to balance. And what you're going to find, guys, common multiples. 6, common. 10 is common. 14 is common. Sometimes 12, but 6 is a big one. Okay? So we look at this, and I have 1 iron, but over here I have 2. So I could start out and say, okay, I'm going to put a 2 here. Now my iron's set. But I have 2 O's here, but 3. Now I need a common multiple. Common multiple 6. So if I put a 3 here, and then a 2 here, this 2 changes that. And now I got to change this. This is no longer good. So I'm going to erase it. And then I'm going to have 4. Okay, that's what I mean by a seesaw. Say I started over here and I saw the 2 and I put a 2 here. Then I went, there's a 2 here and I put 1 here. But now it changes this. So now I got to go back and change this. So back and forth, back and forth, back and forth. You're probably like, oh. But that's how it is. Okay. Let's go to the next example. This one's a little longer. So it's iron 3 sulfate and potassium hydroxide. And I'm going to show you how you predict this. Iron 3 sulfate, potassium hydroxide. Where is my whiteboard? Here it is. Okay, I'm going to clear my whole whiteboard here. Clear my canvas. Iron 2 sulfate. Would be good if I had the right thing here. I thought it was iron 2. I better go check that. Potassium hydroxide. I'm just going to check. Nope, it was iron 3. Silly me. Right, so I gotta go change this. Hold on, my hand's spazzing. Okay. So, oh, come on, stop. So what happens when you get old, guys? I have a pinched nerve in my neck. And because I'm doing so much computer work, when it acts up, literally when I hold my pen, I look like I have Frankenstein hand. It starts to get like a Charlie horse. And it gets so bad I can't hold the pencil. Alright, so iron 3. So this will be a 2 over here and a 3. Now, this is called a double replacement reaction. Little preview of what you're going to need to learn. Why is it called that? Because two ions swap. These two, the two positive ions, are going to switch places. And they swap. So the K goes with the sulfate, which actually becomes a 2. And then you have an SO4. And we'll learn how to know, oh, it's going to be K2. And then the iron goes with the hydroxide. So now I have to balance. What I'll say to you is, focus on these things. See, you have a, what the heck? I'm technically challenged tonight. Focus on that. And I have 1 over here. Well, here's the thing. I got 3 on the left and 1 on the right. So I'm going to go, oh, I'm going to put a 3 here. But if I put a 3 there to balance the sulfates, so I always say keep polyatomic ions together. 3 times 2 over here gives me a 6. So I'm right for now, I'm going to put a 6. I may have to change that. Now I have 6 of these. But over here, I only have 3. So I'm going to put a 2 in front of here. But now I have a 2 in front of the Fe, so I got to come back over here. And I'm like, okay, I got a 2. And if you really wanted to count individual atoms, I have 2 Fe's, 3 S's, 12 O's, 6 K's, 6 more O's, 6 more H's. Right? So I really have, 18 O's on the left-hand side? So let's look at this. 6 K's, 3 S's, 12 O's, and then 2 Fe's. Now be careful. 3 times 1 times 2. Right? 3 times 1 times 2. So that would be 6 O's. Right? Yeah. And 6 H's. Okay, so 6H, 6 O's, 6 K's, 3 S's. Oops, here's 12 O's. I didn't write the O. 12 O, 2 F, E. This is Fe. So I'm balanced. Do you have to do this part down here? No, you don't. Once you get confident enough, you do not have to double check your number of atoms. Okay, so that's what we call balancing equations. Let me go back out of this. So if we look at all of these that are here, you can get through going back and forth and looking at them. Start with yours. Try to balance it. Notice on this one, I started with a 2 in front of the Fe, and then I crossed it out, and I put a 4. Right? And I went back and forth, and I ended up with 1102. Now, combustion. Balancing combustion is a very stepwise procedure. Right? So you do want to write down your steps, and I'm going to pick the first one, which is C7H16. Oh, it went to big thingy. I'll go even lower. Combustion has O2. We make CO2 and H2O. So a lot of times with combustion, they don't finish out the reaction because you're supposed to finish it out. Okay, a little too thin now. So I always start with C's. I'm going to balance that first. I have 7. I'm going to put 7. Then I'm going to balance H's next. Okay, so that's the next step. 16. But there's a 2 here. So what times 2 equals 16? 8. Now I'm going to count O's. Count O's. 7 times 2, 14. plus 8 times 1, 8. I add them up. 22. Whoa, bingo, this is even. Yes, because even can be divided by 2. When I divide by 2, I need an 11 over here. Phew, that's good. If it's not even, I'm just going to look at this first one, C2H2. You have to do an extra step. Again, you should get used to not seeing anything on the right and automatically writing CO2 and H2O. When you have to take your predicting reaction quiz, it's all about predicting. I give you a word equation that tells you you're combusting C2H2, and that's all I tell you. And you have to give me the rest and have to balance it. So I'm going to go through. Start with the C's. 2. Then I'm going to move to the H's. 2. I'm not going to touch anything. This is already 2. Now I count O's on this side. 2 times 2 is 4. And then I have 1, and that's 5. Bummer. Because if I wanted to do this, right, I'd have to divide by a 2, and this would be 5 halves. But AP hates that. They want a whole number here, so you multiply everything through by 2. So then this becomes 2 C2H2 plus 5 O2. Now don't forget, 2 times that, 4 CO2 plus 2 H2O. See how I took this particular equation and I multiplied everything by 2. So in the notes it says double it and then fix your O's. So make sure your O's are the right number. Okay? Now, here's a tricky one. And it's not on your notes. Clear air canvas. Let's do C2. I gotta think how many H's are in here. H5. OH. Look what's in this one. An O. Now it kind of messes up our balancing. But it's still kind of the same procedure. I balance. C is first. 2. 2. H is next. Notice 5. 1 is 6. Ooh, sorry about that. Come back. Ah! What the heck? Okay. I think that's good. Nice and big for you to see. So 5 plus 1 is 6. I'm telling you, it's one of those weeks. So now I have my C's and my H's balanced. Now total these again. 4 O's. 3 times that plus 3. You might go, oh, you're odd. Oh, I am, but look at this guy here. I have to subtract 1. Because what I'm saying is I have a total number on the right-hand side. And my total is 7. But that 7 includes this and this, combined. So I'm going to balance this one out to begin with by subtracting 1. So now I'm at 6. Oh, now I'm even, and I can put a 3 here. Okay, if I wasn't even, I'd multiply everything by 2. Okay, keep that in mind for later. All right, this is balancing. You're going to do lots of practice balancing. Start with a pencil. Don't do it with pen to begin with, because then you get a lot of cross-outs. All right, balancing is balancing mass.